they did something. Okay. They did something that was also very useful for us, meaning that they did a GINS analysis to extract the density profile of the dark matter in these objects. So this we need also for our work, and we take it from there. Okay, what happens? Okay, so the data is like this. It's in the form of a cube. So let's say here we have our dwarf galaxy, and then we have one of these images for all frequency that Muse can see. So what we do is we take the image of this, we take this galaxy, it has stars. We assume that all the dark matter in the galaxy is axions. Some of these axions will decay into photons, and some of these photons will travel towards Chile, and they will be detected by the Very Large Telescope. So we have this image, we mask the sources, as I said, because we're not interested in them. And then we have our data. Then we have to compare it to our model prediction. So we have, this is our expected signal, okay? So we have the axion decay rate here. This depends on G square and on the axion mass to the third. Here we have some detector response. This is basically the spectral resolution of the detector. And then we need to integrate the dark matter density multiplied by the telescope beam along the line of sight and along the solid angle of the beam. And this is the flux density that we expect to observe for given axion mass and for given coupling to photons. So what would a signal look like? So here in blue, we took Leo T, so one of these galaxies that we're using. And for each wavelength channel, we averaged the flux over the pixels, actually the pixels in considering our analysis. And this is the blue part. What a signal would look like is something, for example, the red line or the green line here. So for two different axion masses and coupling. So you can see there's a lot of stuff here that looks like a signal. So these lines are emission lines from our atmosphere that they are in the data even after the sky subtraction. So it's not possible to completely remove them. So, okay, so if we want to put a bound and we want to put a bound in this channel, the bound is going to be weaker because of this line. So it's okay, we are being conservative, but it's more difficult, of course, to claim a discovery in this situation. Many channels are not usable because there's basically just the emission line for the atmosphere. Okay, so this is our bounds, assuming an NFW profile for the 5 galaxies. We get more or less the same bound from all of them. And this is the combined bound, and it goes from 10 to the minus 12 inverse GeV to 10 to the minus 13 here at highest frequencies. Okay, then we also consider a core profile. So here I'm plotting the best fit value from the GINS analysis of the profile of Leo T, assuming NFW is the blue line, and assuming this core profile here, which is core NFW tide. So you see you have a core instead of a cusp. And then there's also a tidal radius beyond which the density drops, but it's not visible in this image because it's further away. So here I'm plotting, this is the distance from the center of Leo T, and this corresponds to the maximum distance that we consider for our analysis. It corresponds to one arc minute on the sky here of a radius. So this is the result for the core profile. It's very similar as the one for the NFW. This may be surprising because if you look at this, you say, well, but here I have more dark matter. Why doesn't this count? Well, because basically because this is at the center, so there are only maybe a few pixels having this dark matter density, but there are a lot of pixels here, okay? And where the two profiles are similar, and these pixels dominate because we calculate the chi-square sum in overall pixels. So this is why these bounds are similar for the two profiles. This is the bounding context. So here on the left, we have our bound. And this line here is the bound from stellar evolution in globular clusters. The yellow is the QCD axion band. And this is a previous bound from observation with VMOS of galaxy cluster, which is basically the same process and just a different observation. And here we have also our bound in dark blue and in cyan, an all bound done also with MUSE previously by my colleagues here at the University of Turin and people from MUSE using only LEOT. So this was the bound you see is gotten worse. This is because in this case, the genes analysis from the MUSE collaboration was not available here. So they had to take the dark matter profile of LEOT from the data of the literature, and this was overestimated. So now the reference bound is the blue one. There are similar other works that do the same thing for different frequency range, different telescopes. So as I mentioned, there's this VMOS paper here from 2007, which is the first one that did this analysis by Green et al. More recently, there was this paper in which they used JWST to put a bound in the near infrared. Here, looking at using blank sky observation that JWST does for sky subtraction purposes. And there's also this paper one, this bound here also in the infrared by using the spectrograph WINERED. Also, there are some forecasts here for use always with the JWST and projection of its sensitivity at the end of its lifetime. Okay. Maybe I can take some questions now before changing topic, if there's anything.
I have a question.
Oh, hi, Nick.
Hello, how's it going? For can I see the radio flux again?
The formula, you mean?
No. So the figure. Here. Oh no, sorry. The previous figure again. The one where you have the flux density.
This.
Yeah, exactly. So why is the flux density negative in places?
I guess this is because here they calibrate this data with their software and they do a bunch of subtractions. I guess this happens when you subtract the emission lines.
Okay, this is the background subtracting. Okay.
Yeah, I think so. Yeah. Okay. If there are no more questions, I will move on to the next part, which is axion simulated decay. And why this image? Because axion simulated decay is a consequence of Bose enhancement, which is the fact that bosons, like you see photons here, Higgs bosons, they like to be together. And the more the merrier. So if you have a lot of photons, they are going to want to have more photons, even more photons, while fermions like to be in a bit more comfortable, spacey situation. Okay, let's go back to the decay rate in vacuum. Now I'm changing frequency range completely. Before I had 4 eV, now I have 10 to the minus 5 eV. Okay, so I'm in the radio or microwave band. And I have here a coupling that is on the QCD axion band. Okay, so now you see this decay rate has become even smaller. This may seem hopeless. Even you're looking at dwarf galaxies, this not enough axions to have actually a signal from with these parameters. But what happens if the decay happens not in vacuum, but in a background? So let's consider this case. I have an axion here at rest, and I have a background of photons. Let's imagine that these photons all have the same momentum k, and they all travel in the same direction, and they have a frequency about half of the axion mass. So what happens is that these photons are going to want to have more photons with them. So the decay rate into photons with this momentum is going to be enhanced. And it's going to be enhanced by a factor of the phase space density of photons with momentum k. Okay, so this is basically the number of photons, of pre-existing photons in the phase space cell corresponding to momentum k. Okay, one can see more, let's say, well, in a simple way, how this happens. So the interaction term, second quantized Hamiltonian here, was going to be something like this. Let's take the term which has an axion at rest. Here you have an annihilation operator for an axion at rest. And I have two creation operators here. One is we create a photon with momentum k, and one a photon with momentum minus k, plus the inverse process. Okay, let's imagine my initial state is like this. So I have to apply this operator. I said to apply this operator on this state. So I have a bunch of axions and I have a bunch of photons with momentum k. What happens after I apply this operator? I lose one axion. I gain one photon with momentum k, which is identical to the pre-existing ones from the background. And I gain one photon with momentum minus k. So importantly, this one is going to travel in the opposite direction as the background photons. And you can see that when I sandwich my Hamiltonian between these two states, and then I square it to calculate the matrix element square, I will be enhanced by a factor of f, or f plus 1, if we want to be precise. Okay. So as I said, one of the photons is identical to the one that simulated the decay, and that one travels backwards, but almost backwards as usual, because the axion has some momentum. So we are in this situation. We have the axion decays. This is identical. This one travels backwards, but it's a bit deviated because of the axion momentum. And this is the photon that we call the echo, because it travels backwards, of course. So how big can this enhancement factor be? So we can relate the photon energy density to a phase space occupation like here. Here I didn't put the, let's consider I have only one polarization. I didn't put the 2 in front of here. Let's imagine we have a beam of photons with a cross-sectional area of 1 meter. I turn it on at some time t. And after some time t, what is this actually doesn't depend, for fixed power, it doesn't depend on t. What is the enhancement factor is about 10 to the 20 if I have a power of 1 kilowatt and a bandwidth of 1 megahertz. So this is already a huge number for 1 kilowatt of power. And here you see this goes like m to the minus 3. Why? So well, you can see it from here. So if I take d rho, d omega, because of this and this omega here, and this thing, and this d3k, d rho d omega is going to go like k omega to the third, which is proportional to m, because we are assuming omega is m over 2. So what about instead radiation that's surrounding our universe? So here I'm taking this plot from this paper by Caputo et al. 2019, in which there they calculated the enhancement factor from CMB, from the extragalactic radio background, from the galactic diffuse emission, from the galactic center. So these are two different integration radii about the galactic center. And you see, even in this case, you can have a large number. And you can see that this, of course, is the lower you go in mass, the more this enhancement factor grows. So as I said, so what happens is that we have this flux densities like this. This is the same as I showed for the spontaneous decay case, which corresponds to this +1. But then now we have a stimulated decay term here. So what happens? We have the decay rate that goes like m to the third. This one we see goes like m to the minus 3. So these two more or less, if this is a constant, these two cancel, and I have a flux density independent of m. This allows me to go to put a bound at low mass, because if I don't have these, the decay rate drops very quickly with as the mass becomes small. Okay, so in this paper that I did with Calore and Regis, we tried to do, we did a detailed study of the echo from a point source. In particular, we used pulsars. So what happens when you have like a point source, let's say a star or something that we idealize as a point source, emits radially and isotropically in all directions. So what can we look at in terms of simulated decay? So the first thing you can look at is you can look directly at the source. And if there is some dark matter between us on Earth and the source, the radiation from the source will simulate the decay of this dark matter, and then we can detect it. Of course, there's a background from the source itself, but in case this has a smooth spectrum, there will be a line on top of it, and we can hope to subtract the smooth part and to isolate the line. This is not an echo. This is the photon that is exactly, so the photon that we receive in this case is the one that is exactly identical to the pre-existing ones, okay? And instead, we can have two kinds of echoes. So this is the backlight echo, which is the most studied case, in which I am here, I have the source on one side, and I look at in the opposite direction. Okay, and then we have the front light echo, in which the source, we look at decay from dark matter situated behind the source from our point of view, because the source also emits in the direction opposite to us, so we can detect this echo from behind the source, which is we call front light echo. Okay, some brief literature review on this topic. These are papers that were out before ours. The first one was this that I already mentioned by Caputo et al. Here they look at the collinear emission at the dwarf galaxy Reticulum 2, and they make forecasts with SKA and HIRAX. Here the simulating radiation is the CMB and the extragalactic radio background. Then there was this one, looking at the echo from backlight echo from the radio galaxy Cygnus A, also forecast with SKA. And here we have two forecasts instead with, this is fast now. I'm not sure anymore what this telescope is. This is with FAST. These are echoes from supernova remnants. And you can see there's some uncertainty band. This is the uncertainty in the modeling of the supernova remnant time evolution and other factors. And here also is two different models for the supernova remnant. Then at the same, a bit before us, at the same time, or let's say at the same time as us, we were working in parallel. There was also this this paper in which they look at the emission from the whole sky. So all possible sources here with some telescopes that survey the whole sky. So we have the synchrotron radiation from our galaxy, we have extragalactic point sources, and the supernova remnants. And then there's also this one. This one came after ours. And here they do a forecast with SKA, looking at the backlight echo from the galactic center. There's also FAST here. Most recently, there was this paper, which is, to my knowledge, is the first one that actually uses real data to put a bound using this method of Axion simulated decay. It falls in a constrained region, but okay, it's the first work. And also they had only 2 hours of observation of this dwarf galaxy with FAST. And I have to say that all these forecasts usually assume 100 hours of observation, while this one is only 2 hours. So I think it's good that some real bounds are coming out using this method. Okay, so what did we do? So we wanted to do a systematic study of the characteristics of this echo from a point source. So here I'm showing this plot. This is a plot of the echo intensity on the sky. So basically this is some dimensionless quantity proportional to the flux density. And here's the observation angle. So let's look at the figure. So for the backlight echo, this is the angle I'm plotting here, okay? And for the front light echo is this one. So how much I displace my observation from the location of the source or the location exactly opposite to the source. So let's look at the backlight echo. No, first let me say this thing. This is an idealized situation, so in which we can actually do this thing analytically, calculate this curve analytically, in which we assume that there's an infinite dark matter halo with a constant density, that the velocity dispersion is a constant across the halo, the source is infinitely old, there's no relative motion compared to us of the source or of the dark matter, and the flux of the source is constant in time. Then you can get this. So for the backlight echo, you see the echo is spread in the sky over an angular distance over the tens of arc minute, which is actually more or less twice the velocity dispersion of the dark matter. And you can see it from here, the backlight echo. So I have this simulating photon travels along this line, hits an axion here, the axion decays, but it has some momentum p, so let's say it deviates the echo photon such that it reaches Earth. And it's the same thing here. Let me mention one thing now, because it will be useful to understand a picture I'm going to show later. So you see here, so the momentum here is pointing in this direction, and it means that my image is deviated along. I have to look. How can I say? So the image I see is going to be in the pointing towards the opposite direction of the dark matter momentum, because it's this is pointing this way, but my image is on this side from this decay. And here we have the opposite situation. In this case, my echo image is going to be deviated in the same direction as the dark matter velocity. Okay, so this is the idealized case without all the effects, with all the assumption I said. In our paper, we introduced them all one by one. So the dark matter density of our galaxy, of course, the corresponding velocity dispersion, which is not a constant across the galaxy, the velocity, the average Almachter velocity due mostly to our motion in the halo, the source's age and the source's proper motion, the source distance, and the source variability in flux. So this is the result for 4 pulsars that we consider to be the most promising. Here I'm plotting the intensity at 400 megahertz. But basically what we want to see from this plot is how the echo is distributed on the sky. This is the front light echo. Yes. So this pulsar here is Vela, which is famous. It's the brightest pulsars we have at radio frequency. At 400 megahertz is about 5 Jansky. And here you have lines. So the blue line, so here we have galactic coordinates on the axis. So the blue line is the projection on the sky of the dark matter average velocity. And the pink line is the proper motion of the source. Okay, so here you see this is quite centered, not perfectly, mainly because of the proper motion. So in the case of the proper motion, the echo is going to be centered in the opposite direction of the proper motion. So it's going to be centered where the source was in the past, along this direction. Here we have another pulsar. This one is a bit less bright, and it has a dark matter velocity and the proper motion velocity pointing more or less in the same direction, as these two effects compensate, right? Because this is going to want to move the center of the image this way, but this is going to want to move the center of the image in the opposite way. So this is quite centered because these two compensate. Then these two, this is quite striking example. Here we have this one. These two pulsars are very similar in flux, similar in distance, and they have a similar dark matter density along the line of sight, but you see that the echo looks completely different. So for this one, we didn't find information on the proper motion. So here I'm only plotting the dark matter velocity. And so the echo is, the intensity is moved in the direction of dark matter velocity. And here, instead, we have a large proper motion here in pink. And you see this also, this is also doing, also wanting to move the intensity on this side. So here you see it's completely non-isotropic, this about the location of the pulsar, this for this one. So in this case, we want to know, if we want to look at this pulsar, at the echo from this pulsar, we want to know that maybe it's useless to look here, we want to look here. To give you more an idea of really how much the flux is suppressed. Here, these are slices through the plot I showed before of at constant galactic longitude and a constant galactic latitude. And you see that the red line here is the last one that has a large proper motion. You see the flux is really suppressed along the galactic latitude direction, which is here. While it's basically only concentrated in this direction here. Okay. So we also did some forecasts. I'm going to show these. I'm going to show them even though they're not very exciting. So here we have colored lines. The colored lines are for the 4 pulsars I showed before. So these assume 100 hours of observation of the single pulsar. And the dashed line is for the front light echo, and the solid line is for the collinear emission. For these 3, we made forecasts using SKA, while this one is in the northern hemisphere, so we use LOFAR 2, so the upcoming upgrade of LOFAR. Okay, we are strongly constrained here, so this is not very exciting. We can also look, so SKA 1 has a survey of galactic pulsars planned. And so we made a sensitivity estimate assuming this survey, which gets a bit better, but still constrained. And then we can touch, if we assume SKA 2 improving a factor of 10 in sensitivity, we can start to touch the here slightly below the constraint from stellar evolution. Okay, so the bounds are not very exciting, but the main contribution of our paper, the forecasts are not very exciting, but the main contribution of our paper was to do the systematic analysis of the signal. And let me get to the last topic. I talk about natural sources like pulsars, supernova renas, galactic center, radio galaxies, but why not use an artificial source? And this was an idea by Ariel Arza and Pierre Sikivie that came out in 2019. And then I also did a work with Ariel on this topic. So we can use an artificial source. We can take our telescope and use it as an emitter and emit a beam of a given frequency, which we assume to be half the axion mass. We assume, okay, we are going to test a mass double that frequency with this, in this case. It will, there's dark matter nearby, some axions will decay, and because this is a simulated decay, there will be an echo coming almost back towards the emitter, almost because of the momentum as usual. So here the issues are the same, basically that regarding the velocity, the relative velocity of the dark matter to us are the same as I discussed before. So we have the K, so here's the beam. So I turn it on at some time t0. At time t, it has a high of t. And the decay happen wherever this beam, in the volume where this beam exists, and they hit ground level where my receiver is, then they will start to spread. See, the more the beam grows, the more it will start to spread. And eventually, I turn off my beam, this cylinder will start traveling away from me, and this will spread all over the place. So at some point, if my receiver has a finite size, these photons are going to start exiting the receiver, so I'm going to lose in the intensity. And this is instead the situation in which we have the velocity, the phase space momentum distribution, the momentum distribution of the dark matter is dominated by a single average velocity. Let's say it's pointing like this arrow. And in this case, also my radiation will at some point exit the receiver and it will go further and further away. And this is the simulation I did for my paper with Ariel of this, of what I just explained. So this is the case of the velocity, the dominated velocity dispersion and negligible average velocity. Turn on the beam, intensity grows. This is the intensity at ground level I'm plotting here. Intensity grows. At some point, I turn off the beam, poof, it disappears. While in this case, I create this sausage that when I turn off the beam, it's going to start traveling away. So it will travel out of the detector. And this is the limitation, actually, of this experiment. We made some sensitivity forecasts for two different models of the dark matter halo of our galaxy. So there's a classical isothermal sphere, and there's this more exotic caustic ring model, which performs better because in this model, the velocity dispersion of the dark matter is very small. So it's 17 meters per second, not kilometers per second. So this is extremely small. And this means that all the power from the decay is concentrated into a very narrow band. So this enhances the signal to noise. So these forecasts are assuming assuming that we use an energy of 10 megawatt per year to cover a factor of 2 in axion mass, signal to noise of 5, noise temperature of 20 Kelvin, and an emitter of 50 meter and a concentric receiver of 100 meter. So you see, okay, let's look at this more conservative model. You can constrain a pretty big chunk of the parameter space. Okay, so this is all I wanted to say. So I talked to you about two different strategies to search for products of axion decay into photons. So the spontaneous decay is for masses of order 1 eV or slightly below or above. And in this case, we don't care that there is a photon background. We just want to look at places where there's a lot of dark matter. While if we go at low frequencies, we want to be in the simulated decay regime. So we want to look at sources that have already a lot of radiation. And we can look at echoes and we can look at this collinear emission. Thank you.
Okay. Thanks, Elisa, for the nice talk. So now we are gonna, if there's someone from the audience who has a question, please feel free to ask. Nick?
Yeah, I have a question. So for the Axion Echo case, have you costed how much it would cost for the electricity for 10 megawatt years?
I didn't, but I believe, Ariel, did you do it at some point?
Yeah,
when you were...
Pierre and I were looking at that, and
Yes, of course, it was before the big inflation also.
Yeah,
So...
it depends on that, and depends also on the country, how much.
Yeah.
Yeah. So in the US, we estimated like $1 million for 1 year.
Okay, that's the thing is the bounds that you present are quite strong, so you could maybe give a more economical version.
Yeah, yeah, that's for a very expensive experiment.
Yeah, maybe if you can get Elon Musk or one of these people interested, maybe he would give you the money. But okay.
Yeah. But okay, $1 million. I mean,
but I think we already contacted the Sanya radar people. So they have the emitters, and but the power is not as much as 10 megawatt. A little bit lower than that, right?
According to Xiaolong, I think it's more or less 10 megawatts. What they have in Sanya.
But presumably that wouldn't be for a whole year, right?
No. It did not last too long. Actually, in order to remove the backgrounds from the ion spheres, maybe we should turn on and turn off, and to pick up the signal and reduce the backgrounds. Because I think all proposals have one problem: the contamination from the ionospheres. This is very, very important. Actually, it is a key factor in those kind of experiments.
Mhm.
Yeah. So actually we are stuck. We are stuck.
We're now addressing this problem with the ionosphere with the fact that for very narrow beam, the axion echo is shifted in frequency respect to the beam and also respect to any echo coming from the ionosphere. So
I actually have a slide for that.
yeah, that's the this is my
Here
main
it is.
for this. Yeah. So
The
this is
slide from our paper, yeah. But we have to see if this is sufficient. Of course, if the echo from the ionosphere is like something like this, then it's gonna also cover.
But the thing is that this shifting is because of the velocity of the axion, which is 200 kilometers per second, and the velocity of the particles in the ionosphere are not that high. So I don't expect the shift from the ionosphere will be that strong.
No, what I'm saying is that this peak is going to be much. So the echo from the ionosphere is going to be much stronger than this one. So maybe if there's some tail, it may. I don't know, maybe it doesn't reach here. But...
That's true. Yeah, but usually the tails decay exponentially. So yeah.
That's true.
So Elisa, I have a question for you. Sorry, another question from the audience.
So I have not a question exactly, but just a comment. So the Meerkat Radio Telescope is having a call for proposals next month. So it might be worthwhile to think about the Axion Echo thing. I don't think you're going to be able to do with Meerkat. They won't let you put a radio transmitter there. But yeah, for the other two things that you talked about, there might be some possibility. Could be interesting.
Yeah. Okay. Thanks. I will have a look at it.
Mm-hmm.
So another question. Okay, so I have two questions. One, okay, both have to do with the background, with the removal of the background in your data analysis. So how
in the
much?
Muse, you mean?
Yeah. Or in general, how much of the sky background you can remove? Or yeah, I mean you can remove it completely or a certain percentage.
So obviously here, so I didn't do this. Okay, so I don't know the technicalities of of this because the people from Muse, the people from Muse did it. Of course, it was not done perfectly. So for example, sorry for the going back and forth. My computer, here it is. So sorry. My computer seems to have issues. Okay. I was going too fast. So here, okay. So here they did the sky subtraction, but these lines, they are so bright that actually we think they saturated the detector, and then it's completely in the that channel is messed, but basically. So this is I don't know how to answer your question very well. They did it as carefully as they could with their data reduction software, still imperfect because these are very bright actually.
But for instance, not taking into account the spikes or so there is in the whole range there is like a fluctuation. So if there is no reduction of the
wait, I didn't say that. So actually we have in our analysis, so we didn't we included a factor to additionally remove the background. So we assume that what we observe is given. So for a given axion, there's the flux from the axion, and then we also assume that there's a constant background across the image, which changes with each wavelength. Okay, so we let this flat term float. So we treat it as a nuisance parameter. Basically, in our analysis, we let it float, and then we profile it out. So besides the sky subtraction that the Muse did, we also include this in our analysis because it may be imperfect. So basically, we remove, if you want, we remove the best fit value of the average flux across the image for each channel. Yeah.
I see. Okay, so the other question is respect to the collinear emission of the stimulated decay. So since you always, I mean, in this case, you have always a strong background, which is the stimulator, right? The one that is stimulated, right? So why the signal depends on the source if you always have, let's say, I mean, the proportion between the new photons and the old photons are they like similar? I mean, the proportion of the, I mean, the ratio between the new photons over the old photons, it's always similar, or it has some.
You mean for different sources?
Yeah. If you change the source, the proportion.
Okay, of course. Well, it depends on. I think so. It depends on how much dark matter you have between you and the source. So of course, if the source is very close, you don't have much integration range, you know. So and then so why not look at the sun? Yeah, I know you also try to do this, like, because it's too close, right? There's not enough dark matter there. So I think that's what can make the difference in this case of the collision.
That makes the difference, but that makes also the difference. I mean, that makes a difference if we consider both cases, stimulated decay and spontaneous decay. But for stimulated decay, it's not a problem. Why there is an advantage that you have something that it stimulates the decay, because you have also this source, like a noise, like a very strong noise, right?
Yeah, of course. For our forecast, we assume that when you look at the collinear emission, there's only forecast, there's no real data. So all these forecasts assume that you're able to subtract the background. And this assumption may be optimistic. I agree.
Yeah, I see.
Yeah.
Okay. Yeah. That's all for me. And anyone has another question? Okay, if not, then we can finish the seminar. So thank you very much, Elisa, for
Thank you for inviting me again.
Yeah, so see you soon, I guess, in the summer.
Yes. See you soon. Bye.
Bye-bye. Have a nice day.
Thanks. Bye.
Bye.
Bye-bye.